Imagine trying to fit an entire, enterprise-grade relational database into a handful of plain text JSON files.
Oh, man.
Right, like complete with multi-table entity relationships, strict data schemas, atomic locking mechanisms, and military-grade encryption.
Most veteran developers would just laugh you out of the room if you pitched that.
Exactly. They tell you it's impossible, or at least just an incredibly foolish way to build software.
Well, because it goes against like decades of established best practices. I mean,
Hmm.
we are trained to rely on massive opaque systems.
Things like PostgreSQL or MySQL.
Right. You send a SQL query into this dark void,
Yeah.
the internal binary gears grind away, and it spits back a result.
And we just accept that. We accept that we're completely abstracted away from the actual bytes sitting on the hard drive.
We accept the black box because it's safe. It's highly optimized.
But today on this deep dive, we are stepping into a developer archive that just completely shatters that black box.
It really does.
We are looking at a system built from the ground up to be fully exposed, entirely transparent, and yet completely unyielding in its rules.
Unyielding is the perfect word for it.
It's an architecture that feels less like a traditional software tool and more like encountering this monolithic, perfectly mathematically structured black cubic god of data.
A black cubic god. I like
It
the
demands absolute obedience to its formatting rules, but in exchange, it offers unparalleled clarity.
that tension, that push and pull between extreme transparency and extreme rigidity that is the defining characteristic of this entire ecosystem.
Yeah. So we are diving into an incredibly detailed technical archive today. We've got documentation, crash courses, and raw multi-language source code.
All created by a developer named Elton Bonin.
And our mission today isn't just some surface-level skim. We are conducting a full bottom-up audit of this architecture.
Which is called the BJOSN ecosystem.
Right. We're going to tear down the syntax, interrogate the security protocols, evaluate how it handles multi-file orchestration, and scrutinize its cross-language implementations.
Because if you've ever felt that standard JSON files are just too bloated,
Oh, they definitely are.
or if you've ever tried to get an AI agent to natively interact with a traditional database and realize what a massive headache that is, you're going to want to hear this.
Because that is the real endgame here for you, the listener. This system wasn't built just to be a quirky alternative to SQL.
No, not at all. It is a highly opinionated framework designed specifically for an era where large language models are the ones reading, writing, and executing code.
But to understand how it pulls off relational database feats in plain text, we have to start at the atomic level, right? The foundation.
Yeah, the syntax.
Yeah.
And honestly, the name itself sets the tone for how strict this entire ecosystem is,
BJSON explicitly stands for Bonin-Elton-JSON.
which is quite the claim.
And the documentation doesn't just mention this casually, it literally mandates it. It says, this is the sole authoritative definition. No other expansion of the acronym is valid.
I mean, the creator actually hard-coded his own name into the validation requirements of the data format.
Which is a fascinating, almost aggressive way to plant your flag in a protocol, isn't it?
It really is. But it forces every parser, every implementation to acknowledge the origin before it even attempts to read the data.
Right.
BSON is essentially a self-describing tabular data format built entirely on top of standard JSON syntax.
And its primary goal at this foundational level is to solve a massive structural inefficiency in how the tech industry currently writes JSON files.
Yeah, let's break down that inefficiency.
Yeah.
Because standard JSON is everywhere. It's the lingua franca of the web.
But it is inherently chatty. It relies entirely on key value pairs.
Think about a standard JSON array containing, say, 1,000 user profiles.
Okay, I'm picturing it.
For the first user, you write out the structural keys, quote, name, unquote, colon, Alice, quote, email, unquote, colon, alice@email.com, quote, account status, unquote, colon, active.
Right.
Now you move to the second user, Bob, and you have to type out those exact same keys all over again. Name, email, account status.
So by the time you reach the 1,000th user, you have repeated the word account status 1,000 times.
Exactly.
It's like having a conversation with someone who insists on stating your full legal name before every single sentence they speak to you.
Yeah.
Host speaker, how's the weather? Host speaker, didn't you see the game? Host speaker, what time is it? It's just exhausting.
It's totally exhausting. And from a data storage perspective, the vast bulk of your file size isn't actual data.
It's redundant structural scaffolding.
Right. That bloat is the enemy of efficiency, especially if you are passing these files back and forth to an LLM with a strict context window limit.
And Bayes solves this by enforcing what it calls positional integrity.
Positional integrity, yeah. It takes the concept of a meticulously organized spreadsheet and just forces it into the JSON standard.
Instead of scattering keys throughout the entire document, a Bayes file isolates them. You have a single array at the very top of the file named fields.
Which acts as your frozen header row.
Exactly. It declares the columns and their associated data types for the entire document.
And following that, you have a values array. But the records inside this array are no longer JSON objects with keys.
They're just raw, flat arrays of data.
The critical mechanism here is that the data in each individual record must perfectly, flawlessly match the index order of that master fields array.
So if the fields array lists email at index position 2,
Then the string at index position 2 and every single record below it is intrinsically understood to be an email address.
okay, let's talk about the mechanics of opening one of these files. Because you can't just throw a fields array and a values array into a text document and expect the bjson parser to accept it, right?
No, no. The system acts like a bouncer at an exclusive club.
Right. There is a strict checklist of 6 mandatory top-level keys that must be present and perfectly formatted.
And if you misspell a key or put them in the wrong order, the parser doesn't try to guess your intent.
It just crashes.
It rejects the payload outright. You must include format, which has to be the exact string, bjson.
You need format version?
You need format creator, which, as we noted, must be exactly Elton Bonin.
Right. Then you define your records type. And finally, the actual meat of the document, the fields and values arrays.
Those are the non-negotiable pillars holding up the black cube.
But the documentation details 3 distinct variations or versions of this format that dictate what you can actually put inside those arrays.
Yeah, we have versions 104, 104A, and 104DB.
Let's pull those apart. Version 104 is like your high throughput workhorse.
This is what you use when you are dumping application logs or massive streams of sensor data.
The constraint here is that a 104 file can only contain one single type of record. It's a monolithic block of homogeneous data.
Right, a file's either 100% user logs or 100% temperature readings.
But it allows for complex nesting, right? So within a cell, I could have another array or a full JSON object.
You can, yeah, but you cannot add any custom metadata at the top of the file. You get the 6 mandatory keys, and that's it.
It is an uncompromising pike of raw data.
The only built-in exception is a key called parent 3R key, which becomes critical when we look at scaling this up later.
Okay, contrast that with version 104A. This variant flips the constraints. It's designed specifically for configuration files, system metrics, or metadata manifests.
It is much stricter about the actual data payloads. In 104A, the values array can only contain primitive data types.
So strings, integers, floating point numbers, booleans.
Exactly. Absolutely no complex nested objects allowed inside the data cells.
But to make up for that, it lets you customize the top of the file. You can add custom headers, provided they use Pascal case formatting.
Right, so alongside the mandatory keys, you could inject a key like server environment set to production.
Or maximum retries set to 5.
Yeah, it gives the file the ability to describe its own context to whatever system is reading it.
Which naturally brings us to the third, and frankly the most controversial variant in the entire archive version, 104DB.
The DB signifies database, obviously.
And this is bjson's attempt to cram a multi-entity relational database into a single text file.
This is where things get wild. In versions 104 and 104A, a file only holds one type of thing.
But in 104DB, the ecosystem allows you to mix entirely different entities in the same values array.
You could have a row representing a user account sitting right underneath a row representing a shopping cart item.
From an architectural standpoint, mixing record types in a system that relies on a single master header row creates an immediate logical conflict.
Yeah, how does the parser know which row is the user and which row is the item?
The system introduces a discriminator field. The very first column defined in your master fields array must be named record type parent.
Consequently, the very first piece of data in every single row tells you what entity that row belongs to.
That solves the identification problem. But it introduces a massive spatial problem. Because of positional integrity, the length of every single record in the file must perfectly match the total length of the fields array.
And here's where you have to throw a flag on the play.
Yeah, if I have a single fields array for the entire file, that means I have to define all the columns for a user and all the columns for an item and all the columns for an order, all in one giant, massive master header.
That's the reality of the design. Every field across all entities is amalgamated into a single schema.
But a user entity doesn't have an item weight attribute. An order entity doesn't have a user password hash attribute.
Right.
So when I go to write a user row, what do I put in the column designated for item weights?
You pad it. This is the concept of null padding.
Null pad.
Whenever you write a record for a specific entity, any column in the master schema that belongs to a different entity must be explicitly filled with a JSON null value.
You are injecting empty space just to maintain the geometric squareness of the overall data grid.
Exactly. Let's scale that up in our heads.
Okay, if I'm building even a moderately complex app, I might have 20 different entities in this database. Each entity might have 10 distinct fields.
That's a master header with 200 columns.
When I write a single user row, which only uses 10 of those columns, I am forced to write 190 null values just to complete the row.
It creates a massive sparse matrix.
Doesn't that completely defeat the purpose of avoiding JSON bloat? We got rid of repeating keys just to fill the file with an ocean of empty nulls.
The file size is going to be like 95% empty space.
So why on earth would anyone engineer it this way?
Well, your skepticism is entirely validated by the source documentation itself. The creator, Elton Bonin, doesn't hide this flaw.
Oh, really?
Yeah, the crash course documents explicitly state that due to null padding, 104 DB files grow exponentially with every new field and every new record you add.
It openly admits that for large-scale storage, this architecture is completely unviable.
Right. It is strictly recommended for under 10,000 records.
So again, why build it?
Because of the O1 parsing speed and the specific use case of AI integration.
Let's unpack O1 parsing for a second. What does that actually mean under the hood for someone who might not know?
So in computer science, Big O notation describes how long an algorithm takes to run based on the size of the data. When you parse normal JSON, the computer has to search for strings.
If it wants the user's email, it has to scan through the document character by character, looking for the string email, and then extract the value next to it.
That's a linear search. The more data you have, the longer it takes.
Like trying to find a specific word in a massive novel by reading every single page.
Exactly. But with Bayeson's positional integrity, the parser maps the master fields array into memory exactly one time when the file opens.
From that moment on, the computer knows that email is simply at memory array index position 4.
Right, and O1 means constant time. Whether there are 10 rows or 10 million rows, the computer can instantly jump to index 4 at a microsecond.
It completely bypasses string searching. The CPU overhead drops to near zero.
Okay, I see the trade-off. You are willingly sacrificing hard drive space, which is cheap, to achieve blindingly fast CPU processing, which is valuable.
And if you hand a 104 DB file to a large language model, the LLM doesn't have to navigate a complex labyrinth of nested objects.
It just reads the master header, understands the entire relational universe of the database instantly.
And can see how all the entities align in a perfect, albeit wide, grid.
It prioritizes transparency and structural perfection over ultimate compression.
But as we established, 104 DB hits a mathematical wall quickly due to that exponential null padding. If you have a real application with hundreds of thousands of records, 104 DB will choke your system.
Which means we need a way to scale this concept out. How do you keep the transparency of Bayesian but ditch the null padding?
You have to split the entities into their own files.
And that introduces the orchestration layer of this ecosystem, the MFDB architecture.
MFDB stands for multi-file database. And now the documentation makes a very sharp distinction here. MFDB is not a new syntax.
There is no format version MFDB.
That's a critical point. MFDB is purely an orchestration strategy. It is a set of rules for taking existing BJSON 104 and 104A files and networking them together across a standard computer file system so they act as a unified relational database.
Let's walk through how this looks on a hard drive. If I open an MFDB project, what is the first thing I see?
You'll see the manifest. At the root directory of your database, there must be a file named 104a.mfdb.bjson.
This file acts as the central registry, the air traffic controller for the entire database.
Inside this manifest, you will find a list of every entity that exists in your database, the relative file paths pointing to where their specific data files live,
The total number of records they currently hold, and their specific schema versions.
So the manifest is the map. Then, maybe in a subfolder called entities, I have my actual data files, users.bjson, orders.bjson, products.bjson.
And because these are standard BJSON 104 files, they only hold one type of record. Users.bjson only hold user data.
Which means the null padding problem is instantly solved. You are back to perfectly dense, efficient data storage.
But here is the challenge. The operating system just sees a bunch of random text files in a folder. How does the BJSON ecosystem know these files are part of a unified database?
This is where that single built-in exception for version 104 comes into play. Earlier, we noted that 104 files don't allow custom headers except for one specific key parent hierarchy.
Right. Inside your users.bjson file, that parent hierarchy key contains a relative file path string pointing directly back up the directory tree to the 104a.mfdb.bjson manifest.
It creates a bidirectional tether. The manifest points down into the subfolders to find the entity files, and every entity file points back up to the manifest to declare its allegiance to the database.
The elegance of this design is in the discovery algorithm. The expert notes highlight that the database engine uses file local discovery.
Meaning it doesn't have to scan the entire hard drive looking for files?
Right. Traditional systems might have to recursively scan every subfolder in a directory to build an index of available files, which is a slow, heavy disk operation.
MFDB bypasses this entirely. The engine opens the manifest, reads the exact paths, and targets the files directly.
Conversely, if a standalone developer tool opens just the users.bjson file, it reads the parent hierarchy key, realizes it is a subordinate part of a larger MFDB system, and can automatically follow that path up to load the master manifest and contextualize the data.
But what happens if I mess with the file system? Let's say I go into the File Explorer and drag users.bjson out of the database folder and drop it onto my desktop.
I've broken the relative path.
Yeah, the parent hierarchy string no longer points to a valid manifest. Does the file corrupt?
No, and that's the brilliance of using a self-describing standard. The parser simply degrades the file into an orphan state.
It loses its relational privileges. It can't join with the orders table anymore, but it remains a perfectly valid, readable BJSON 104 file on its own.
You can still open it, parse it, and read the user data. It's a highly resilient design.
Okay, I follow the file linking. But if we are building a relational database, we need relationships. I need to be able to say that order number 500 in the orders.bjson file belongs to user number 42 in the users.bjson file.
Normally, a SQL engine manages foreign keys with strict binary constraints.
So if these are just disparate text files, how do you prevent absolute anarchy?
It relies heavily on convention and explicit naming structures. The ecosystem manages foreign key relationships without a background SQL engine by enforcing a strict suffix rule.
If a column name in your fields array ends with "a", for example, user@fk, that is a hard-coded signal to the BJSON parser and to any AI reading the schema, that this specific column references a primary key in a different entity.
So the manifest declares that the user entity has a primary key named userid. When an LLM looks at the order entity and sees userid_fisk, it instantly understands the conceptual bridge between those two separate files.
Yes. Now, to be clear, the low-level BJSON parser won't crash if you put a non-existent user ID into that field. It doesn't enforce the referential integrity at the moment of writing.
But the convention provides a perfect programmatic roadmap for higher-level tooling or autonomous AI agents to load those disparate files into memory and perform complex relational joins natively.
This brings up a massive philosophical question. We are essentially talking about reinventing the database, but tools like PostgreSQL are incredibly optimized.
They use B-trees, advanced page caching algorithms, predictive query optimizers.
MFDB is, at its core, a collection of text files pointing at each other. Why rebuild the wheel in such a seemingly rudimentary way?
It's a paradigm shift aimed entirely at the future of development. We are entering an era where AI agents are writing the code and managing the data.
Large language models are brilliant at pattern recognition, but they struggle profoundly with opacity.
When you ask an LLM to interact with a traditional SQL database, you have to build API layers, or you have to trust the LLM to write raw SQL strings, which often leads to hallucinations or destructive malformed queries.
But with MFDB, there is no intermediary layer. You just hand the AI the raw text of the manifest and the entity files.
The AI reads the exact structure of the data, natively understands the foreign key mappings by looking at the string suffixes, and if it wants to update a user status, it just rewrites that specific string in the JSON array.
You are empowering the AI to become the query engine itself, operating directly on the raw state.
It's a trade-off of absolute machine transparency versus ultimate binary compression.
I see the vision. But let's ground this in reality for a second. If I have an MFDB database spread out across a root folder and a dozen subdirectories, how do I deploy it?
If I want to send this database to a client or push it to a cloud server, I can't just attach 50 separate JSON files to an HTTP request and hope the folder structure survives.
Deployment logistics are a huge hurdle for multi-file systems. To solve this, the ecosystem includes a standardized utility known as the chunking engine.
The goal here is to take an entire MFDB directory structure and compress it into a single, highly portable file.
But crucially, it does not just use a standard .zip or .tar archive, it forces the archive data back into the JSON paradigm.
The chunking engine generates a chunked 104A file. It uses the configuration variant of JSON to act as a custom archive format.
The meta nature of the system is wild. The data about the files becomes data within a JSON file.
Exactly. The fields array in this chunked file defines columns for file name, file extension, relative path, and file content.
The engine loops through your database folder, reads users.bjson, escapes all the characters, and dumps the entire contents of that file into a single massive string cell inside the chunked JSON file.
And the archive documentation highlights a major evolution here, the MFDB 1.32 extension.
Yes, prior to 1.32, the community was relying on standard zip containers to bundle the manifest and entities.
But the 1.32 update empowered the chunking engine to package everything manifest, schema, entity data into one pure JSON document. It bypassed traditional compression algorithms entirely.
Which means you can send a multi-table relational database as a single JSON payload to an API endpoint, and the receiving server can unchunk it back into a fully functioning multi-file directory structure.
That's incredibly powerful. But there is a glaring, obvious problem here.
The binary problem.
Right. If the chunking engine operates by reading a file and converting it into a UTF-8 string to put inside a JSON cell, what happens when it hits a file that isn't text?
What if I have a compiled .exe file or a .png logo image sitting in my project folder?
This was a catastrophic flaw in the early versions of the tool. The sources show this wasn't addressed until a critical update on July 14, 2026.
Before that fix, when the chunking engine encountered a binary file, it would try to parse it as text, hit a wall of invalid byte sequences, fail silently, and just write an empty string into the archive.
The binary files were just vanishing during deployment.
It's like hiring a moving company that only provides standard cardboard boxes. You pack your books, your clothes, your text files, they fit perfectly.
But then you have your liquids.
Shampoos, expensive olive oils, your binary files. The movers look at the liquids, realize they don't fit the cardboard box profile, and instead of finding a solution, they just throw them in the dumpster.
You arrive at your new house, unpack, and realize all your liquids are gone.
It was a silent, devastating loss of data. So the July 14 update introduced the equivalent of specialized leak-proof containers specifically for those liquids.
Walk me through the mechanics of that fix. How do you safely put binary liquid into a JSON cardboard box?
The chunked schema was updated to include a new Boolean field named isBinary. Now, when the engine reads a file, it tentatively attempts a UTF-8 text decode.
If it throws an error, meaning it hit raw binary bytes, the engine intercepts that error and flips the isBinary flag to true.
And then what does it do with the raw bytes? You can't put raw bytes into JSON. It will break the syntax with null characters and unescaped quotes.
It runs the raw bytes through a base64 encoding algorithm.
Let's explain base64 for a second, because it's the magical bridge between the binary world and the text world.
Base64 takes any sequence of binary data, no matter how complex or unreadable, and translates it entirely into a subset of 64 safe, printable ASCII characters. Uppercase letters, lowercase letters, numbers, and a couple of symbols.
So a complex image file gets translated into a massive block of text that looks like gibberish, AB3x9QP, and so on, but it's entirely safe to inject into a JSON string.
Exactly. The engine stores that massive base64 string in the file content column.
When the archive reaches its destination and the unchunking process begins, the system checks the isBinary flag.
If it's true, it knows not to just dump the string onto the hard drive. It runs it through a base64 decoder, translating the safe text back into the original raw binary bytes, and perfectly reconstitutes the image or executable on the new system.
It's a brute force solution, sure. Base64 increases the file size by about 33%, but it ensures that the JSON structure remains immaculate and your data survives the transit.
And speaking of data survival, we need to talk about the most dangerous aspect of plain text databases. We are moving into our audit of security, integrity, and locking.
This is where the black cubic god theme stops being a metaphor and becomes a functional reality.
If you have a system built entirely on plain text files, and you have multiple AI agents or cron jobs trying to read and write to those files simultaneously, The risk of data corruption is astronomical.
Imagine a scenario. Agent A wants to update a user's email address. It opens users.bjson, reads the data, changes the email in memory, and starts saving the file back to the hard drive.
But at that exact millisecond, Agent B decides it needs to read the user list. It opens the file while Agent A is only halfway through writing it.
That is a classic race condition. Agent B gets a half-written, corrupted file with a missing bracket, the JSON parser panics, and the entire application crashes.
How does the BJSON core prevent a plain text file from imploding under concurrent traffic?
It relies on a hyper-strict enforcement of atomic operations, specifically routed through a core function called BJSON core atomic write.
When a system requests to save a file, BJSON completely forbids direct overwriting. It will not touch the original file.
That makes sense. If the server loses power while overwriting, the file is corrupted permanently.
Exactly. So instead, the engine generates a temporary file right next to the original in the same directory. It writes the entirely new JSON payload into this temporary file.
But it doesn't stop there. Once the write is complete, it invokes a low-level operating system command called os.fsync.
Why is fsync necessary if the code says write to file? Isn't it written?
Not immediately. Operating systems are clever. To speed up performance, they often hold file writes in a temporary memory buffer in RAM, planning to flush them to the physical hard drive later.
If the server crashes while the data is in RAM, it's gone.
os.fsync grabs the operating system by the collar and says, no, do not buffer this. Flush these bytes out of RAM, emphatically write them onto the magnetic platters or the silicon chips of the drive right now.
And it pauses the program until the hardware controller sends a signal back confirming, yes, the electrons are permanently trapped on the disk.
Precisely. Only after that hardware-level confirmation is received does the engine execute an atomic replace command. It swaps the temporary file over the original file in a single, indivisible operating system tick.
It's an all-or-nothing transaction. The file either updates flawlessly or the old version remains perfectly intact. There is no middle ground.
But atomic writes only solve the problem of how a file is written. It doesn't solve the traffic jam of multiple agents trying to write at the same time. If Agent A and Agent B both do an atomic write simultaneously, whoever finishes last will overwrite the other's changes.
Which is why the ecosystem implements resilient PID locks. Before any process is allowed to modify a file, it must acquire an exclusive lock. But it doesn't use standard lot files, which are prone to edge cases. It uses a locked-dir directory mechanism.
Why create a whole directory just to signal a lock?
Because on PO6 compliant operating systems like Linux or Mac OS, creating a directory is an inherently atomic hardware operation.
If two completely separate scripts try to execute an MOTR command for the same directory name at the exact same microsecond, the operating system kernel guarantees that only one will succeed.
The second script will receive a hard file exist error. It is an unhackable hardware-level mutex.
Okay, so the winning script creates the lockdir, effectively locking the database. Inside that directory, it writes a small metadata file containing its process ID, its PID, and a timestamp.
It does its work, atomic writes the data, and then deletes the directory to release the lock. Beautiful.
But let's break it. What if the script encounters a catastrophic error? A segmentation fault. The server loses power. The script dies instantly before it can delete the .lockdir.
In a naive locking system, that creates a permanent deadlock. The lock directory exists, but the owner is dead. Every other script in your ecosystem will see the lock, politely wait in line, and sit there paralyzed forever.
How does BJSON survive a dead process?
It employs a heartbeat mechanism. If a script wants to lock a file but sees a lockdir already exists, it doesn't just wait blindly.
It opens the metadata file inside the lock directory and reads the PID of the process that claims to own it.
Then the waiting script sends a signal 0 down to the operating system kernel.
What is signal 0? Is it trying to kill the other process?
No, it's more like a systemic ping. Signal 0 asks the OS kernel, hey, I have this process ID. Is this program actually still alive and running in memory?
If the kernel responds no, that PID terminated unexpectedly, the waiting script instantly knows the lock is an abandoned ghost.
So the PID lock acts like a hotel do not disturb sign on a door, but with a built-in heartbeat monitor patched into the guest.
If the guest inside suddenly flatlines, hotel management automatically unlocks the door so the room isn't permanently cordoned off.
A morbid analogy,
Yeah.
but incredibly accurate to the system state. The engine automatically reclaims the lock, purges the dead metadata, writes its own PID, and ensures the database maintains forward momentum despite catastrophic failures.
That handles internal integrity. But what about external threats? These are plain text files. If I have sensitive customer data, how is it protected from a bad actor who just opens the folder?
The archive details a highly sophisticated crypto-utils library built directly into the core engine. It refuses to farm this out to third-party dependencies.
When you encrypt a BJSON record, the system utilizes PBKDF2 for key derivation.
Let's translate that. PBKDF2 stands for Password-Based Key Derivation Function 2. Why is derivation necessary? If I have a password, why can't I just use it as the encryption key?
Because human passwords are mathematically terrible. They're too short, too predictable, and lack the necessary entropy for secure encryption.
PBKDF2 takes your password, mixes it with a random cryptographic salt, and hashes them together.
But the BJSON implementation doesn't just do this once. It forces the algorithm to iterate exactly 100,000 times using the SHA-256 hashing protocol.
100,000 hashes. Hashes the password, takes the output, hashes the output, and does that 99,998 more times. That sounds agonizingly slow.
It is entirely by design. It's a technique called key stretching. Imagine a hacker steals your database and tries to brute force the password by throwing millions of dictionary words at it per second.
If it takes even a fraction of a second just to drive the key for one single guess, because of those 100,000 iterations, brute forcing becomes computationally unfeasible. It's a massive speed bump for attackers.
And once that mathematically complex key is generated, what algorithm actually locks the data?
The payload is encrypted using AES GCM with a 256-bit key length. AES is the advanced encryption standard, the gold standard used by global banks.
But the GCM part is what's crucial here. It stands for Gullius Counter Mode.
Why does the mode matter?
Standard encryption provides confidentiality. It scrambles the data so you can't read it. But GCM provides confidentiality and authenticity. It attaches a cryptographic tag to the data.
If a hacker opens the plain text BJSON file and changes even a single letter of the encrypted string in an attempt to corrupt the data, the GCM decryption process will check the tag, realize the data was tampered with, and hard fail.
It guarantees the data you decrypt is the exact data you encrypted.
But wait, if deriving the key takes a fraction of a second due to the 100,000 iterations, what happens if I need to decrypt a database table with 5,000 rows? Do I have to run the key derivation 5,000 times? That would completely destroy the performance of the system.
It would bring it to a crawl. The source code addresses this by implementing an in-memory key cache scoped per session.
The heavy PBKDF2 derivation is executed exactly once when the database session initializes. The resulting pure AES key is held securely in volatile memory.
So subsequent operations on the 5,000 records happen at the blazing hardware-accelerated speed of native AES GCM.
Evaluating this security posture holistically,
Hmm.
it is striking. We were looking at atomic OS-level flush commands, resilient hardware-level mutex locking, and enterprise-grade cryptographic stretching, all applied to a glorified text file format.
It demonstrates an obsessive level of engineering rigor that you usually only see deep inside the binary core of an Oracle database.
It reinforces the core philosophy. The structure may be a simple JSON array, but the enforcement of its integrity is absolute.
Which provides a perfect bridge into the implementation audit. Because an architecture is entirely useless if developers can't interface with it. And here is where the rules of the BJSON ecosystem become incredibly demanding on its contributors.
Yes, the governance documentation mandates a strict language parity rule. It dictates that the core family of libraries, the code that handles parsing, locking, and MFDB orchestration, must be implemented with one-to-one feature parity across 4 distinct environments.
Python, JavaScript, TypeScript, and Shell Bash.
Python, JS, and TS make complete sense. Those are the dominant languages of the modern web and backend servers. They handle JSON natively. But Bash, the terminal shell language, writing a complex relational database parser in Bash sounds like absolute agony.
It is a monumental undertaking. The prompt requires us to give a praise good bash bad overview evaluation based on the source code. Let's start with the praise.
A lesser developer would have written this Bash implementation as a nightmare of string manipulation, chaining together tools like grep and awk to blindly hunt for quotation marks and brackets.
And that approach would have shattered the core philosophy of BASIN, which relies entirely on structural positional integrity. Instead, the Bash scripts aggressively and intelligently mandate the use of a tool called JQ.
For listeners who haven't spent time in the terminal, what is JQ and why is it so important here?
JQ is a lightweight, command-line JSON processor. It is not a text search tool. It is a full, robust parsing engine.
When the Bash script needs to extract the third column of the values array, It pipes the file into JQ. JQ actually compiles the JSON into a structural tree in memory, navigates to the precise index, and returns the data safely.
So it respects the data structure natively, preventing accidental string matches from corrupting the parsing logic. The reliance on JKey is a lifeline.
It's the only conceivable way a bash script can enforce Bayes's strict validation rules without collapsing into a pile of regular expression errors.
Exactly. The Bash implementation gets high praise for leaning on the right tool for the job, but there is a significant quirk or a bad aspect to how these Bash libraries are written.
Let's get into the weeds of bash scripting. When you are writing a robust, professional bash script, standard best practice dictates that you place a specific command at the top of your file set or noun set.
Correct. Nounset tells the Bash interpreter to adopt a strict execution mode. If the script tries to use a variable that hasn't been explicitly defined, Bash will immediately throw an error and halt execution.
It's a safety net for typos. If I create a variable called username, but later in the script I accidentally type echo error's name, normally bash would just silently echo an empty string, which could cause catastrophic bugs later on.
With Nounset active, the script crashes and warns me about my typo immediately.
But the source code comments for the BGS and bash implementation explicitly note that they intentionally omit set and noun set.
Why would you intentionally strip away a critical safety feature in a library designed to read a database?
Because of the context in which this code runs. These are library files. They are meant to be imported or sourced by other developers' scripts, not run independently.
Ah. And in Bash, if an imported library turns on a global shell option like nounset, it alters the execution environment of the host script that imported it.
Precisely. If a junior developer writes a quick bootstrapping script that relies on undefined variables, returning empty strings, which is sloppy but common, and then they import the bjson library, the Bayesian library would turn on nounset globally.
It would suddenly, unexpectedly crash the developer's script.
That is a deep level of engineering empathy. The BGSLN developers accept a higher risk of internal typos within their own library code, forcing them to be incredibly rigorous in their testing, specifically to guarantee they don't pollute or break the execution environment of the end user.
It's highly considerate, but it does leave their own internal code base vulnerable to silent string errors if they aren't careful.
I understand the execution, but I have to push back on the fundamental premise. Why build this in bash at all? It seems like a massive waste of resources.
If I'm managing a server, Python is almost certainly installed. Node.js exists. Why not just tell system administrators, if you want to interact with the bjson database on the command line, install the Python package?
If we zoom out and look at the reality of server architecture, Bash's ultimate superpower is its ubiquity. Python and Node.js are external runtimes. They require installation, version management, virtual environments, and dependency trees.
Bash is baked into the deepest fabric of virtually every Linux and macOS server on the planet.
Okay.
Imagine a scenario where a server experiences a catastrophic crash and reboots in a minimal recovery mode. The Python runtime might be corrupted, the network might be down, the server wakes up with nothing but a raw terminal shell.
Because bjson is implemented in pure bash, the system administration scripts can immediately natively parse the database, read the critical configuration files, execute the .lockdir mutexes, and bootstrap the server back to life without needing a single external dependency installed.
I concede the point entirely. The ability to manage an encrypted relational database with nothing but a naked terminal prompt is an incredible operational advantage.
But enforcing that one-to-one parity across 4 languages introduces a massive logistical nightmare for the project maintainers. How do you ensure every developer follows these complex rules across diverse code bases? You can't just put a bullet point in a readme file and hope people remember it.
Which brings us to one of the most mind-bending aspects of this entire archive. We are moving into best practices and governance as data.
The sources reveal that the bjson ecosystem doesn't just manage its developers through wikis or Slack messages. It literally encodes the rules of its own development directly into the database architecture.
It is a deeply meta concept. The governance of the project is itself a queryable bjson database file named metadata.bjson.
Let's break down the structure of this file. It exists at the root of the MFDB directory, and it utilizes an EAV architecture, entity attribute value.
For those unfamiliar, an EAV structure is a way of designing a database that is hyperflexible. Instead of creating a rigid table with a column for every possible property, which leads to massive null padding issues, an EAV structure only uses a few generic columns.
The fields array in metadata.bjson defines columns like record type, library family, language, key, and value.
Right, so if you want to store a property, you add a row. If you look at the values array in the sources, you see rows dedicated to version tracking. The record type is version, the library family is core, the language is Py for Python, the key is current version, and the value is 2.4.0.
That's standard version tracking, very clean. But then we hit the record type labeled rule. This is where developer governance transcends documentation and becomes executable data.
There is a row where the key is language parity required, and the value is the Boolean string true. The attached description explicitly notes, core is the only family required to be implemented in parity across all 4 language systems. Confirmed by Elton Bonin, 2026-07-18.
Think about the automation implications of this. A continuous integration pipeline on GitHub, or an AI agent managing pull requests, doesn't need to read a human-written document to enforce the rules. It can run a native bjson query directly against metadata.bjson.
It can literally interrogate the database. What are the structural rules for the core family? And the database programmatically returns a structured array of mandates.
If a developer submits a new feature in Python but forgets to include the bash version, the CI/CD pipeline queries the rule, sees the parity mismatch, and automatically rejects the code commit.
The governance is alive. Another critical rule encoded in this file is family and Setsura codes.
This is extensively documented in the sources. The ecosystem features hundreds of meticulously mapped error codes, but it strictly forbids centralization.
In a typical software project, you usually have one massive errors.py file containing a giant list of every single error that could possibly happen. bjson outlaws this. It dictates that every library family, core, cognition, gaming, utility must maintain and manage its own strictly isolated error registry.
The sources show specific mappings. Error number 1 is Einvalidation. Error number 36 is EMFDB no parenthirarchy. These belong exclusively to the core namespace.
And we can see Elton Bonin actively enforcing this namespace isolation in the change logs. There is a note where he aggressively moved errors 130 through 159 out of the general core library and cordoned them off into a newly created core nesting family registry. He treats these namespace borders like sovereign territory.
Let's look at error 36 as an example of why this precision matters. EMFDB no parenthirarchy. We discussed the parenthirarchy key earlier. It's the bidirectional link that points an entity file back to the manifest. If that key is missing or corrupted, this specific dedicated error is thrown.
Why is that critical? Because without that key, the file might still parse perfectly as a standalone JSON document, but the MFDB orchestration engine cannot guarantee the integrity of relational joins.
By throwing a highly specific queryable integer like 36, higher-level applications or AI monitors can instantly isolate the exact architectural fracture rather than just crashing with a generic, unhelpful file not found exception.
It's precision diagnostics. Every possible point of structural failure has a dedicated, tracked integer encoded into the governance file. And there is one more fascinating rule documented in the metadata that highlights the power of this system, PMS deprecated.
The value is set to true. The description attached states that the project management system modules are explicitly deprecated, physically moved to an isolated folder, and are actively being rebuilt from scratch. It acts as a hard directive commanding developers not to import or extend those specific files.
Again, the brilliance is in the automation. If a developer ignores the memo and tries to import a PMS module into a new script, a pre-commit Git hook can query metadata.bjson, see the PMS deprecated rule evaluates to true, and block the developer's code from ever merging into the repository.
It represents a massive philosophical shift. We are moving from governance by human convention and social pressure to governance by machine-enforced data state.
It guarantees that the rules of the black cubic god are never ignored because the system physically prevents you from violating them.
We've journeyed deep into the atomic structure of this architecture. We've audited the strict syntax formats, the relational scaling of the MFDB orchestration, the ingenious base64 liquid containers of the chunking engine, the ironclad OS-level atomic security protocols, the incredible rigor of the bash JKey implementation, and the executable governance metadata.
Which means we possess the necessary facts to objectively evaluate the bjson ecosystem in its entirety.
Let's run a formal 1 to 10 rating exercise based strictly on the evidence in the archive. Let's evaluate it across 3 core dimensions: readability and AI readiness, parsing performance, and finally, scalability. I will leave
Ready.
Dimension 1, readability and AI readiness. When we factor in the strict positional integrity, the absolute removal of redundant structural keys, the plaintext nature of the relational FEC links, and the fact that an AI can natively read the schema and the governance rules without needing an intermediary SQL translation layer, I have to give this an uncompromising 10 out of 10.
I am in complete agreement. The system achieves its primary design goal flawlessly. By forcing a rigid, unvarying structure, it eliminates the semantic ambiguity that constantly trips up large language models.
An AI can ingest a 104 dB file and instantly generate a perfect, multidimensional mental map of the data schema. It is mathematically optimized for machine comprehension.
Dimension 2 performance, specifically focusing on parsing speed.
I will rate parsing performance as a very strong 9 out of 10. The architecture brilliantly delegates the initial heavy string processing to the host language's native, highly optimized C-based JSON parsers like json.parse in a Node.js environment.
And as we discussed with the O1 big O notation, once that array is mapped into memory, data retrieval is virtually instantaneous. You are bypassing expensive string matching entirely and simply referencing direct array index coordinates.
The only reason it doesn't receive a perfect 10 is the unavoidable CPU overhead required to validate the strict constraints. Checking for the 6 mandatory keys, iterating through the arrays to verify that the lengths perfectly match the schema, that validation step costs milliseconds. But it is an entirely acceptable price to pay for guaranteed data integrity.
Finally, dimension 3 scalability.
Here's where we must be brutally honest. Based strictly on the documentation's own admissions and the fundamental laws of data geometry, scalability must be rated significantly lower. I would rate it a 4 out of 10.
The evidence supports that low score. The null padding required by version 104.IAB is a critical architectural bottleneck. The documentation explicitly warns that it causes exponential catastrophic file size growth with every new field and record added to a complex schema.
And even when you graduate to the MFDB orchestration layer to separate the entities and eliminate the nulls, you are still bound by the reality of JSON. You are fundamentally loading entire tables into system RAM as text objects.
Exactly. This architecture is not and will never be a viable replacement for massive cloud data warehouses like Snowflake or an enterprise Postgres cluster running horizontally sharded data. It is physically incapable of handling billions of rows efficiently.
So, synthesizing those ratings, what is our final holistic conclusion on the BJSON ecosystem?
BJSON is a highly specialized, expertly engineered, and deeply opinionated tool. It is a masterclass in constraint-driven design. It willingly sacrifices infinite scalability in order to achieve absolute data transparency, cross-environment ubiquity via terminal shells, and flawless native integration with AI autonomous agents.
We return to the imagery of the black cubic god. It does not aspire to hold the entire internet's data. It wants to hold a specific, focused domain of data, and it wants to hold it with absolute mathematical perfection, governed by unyielding rules woven directly into its fabric.
If you respect its boundaries and play by its rules, it provides an unparalleled environment for rapid, secure, and AI-native development.
We've covered an immense amount of ground today. We started by dissecting the strict syntax, exploring how positional integrity solves JSON bloat, and analyzing the distinct use cases for versions 104, 104A, and the null-padded 104DB.
We tracked how the system scales into the MFDB orchestration layer, using file local discovery manifests and relative parent hierarchy paths to construct relational databases entirely without SQL engines.
We examined the deployment logistics of the chunking engine, highlighting how the critical 1.32 update solved the binary loss problem by utilizing base64 encoding to create safe, text-based transport mechanisms for raw executables and images.
We rigorously audited the security posture, breaking down the mechanics of atomic OSS.fsync writes, the brilliant resilience of the signaller's heartbeat PID locks, and the massive computational speed bumps created by 100,000 PBKDF2 iterations paired with AES GCM authentication.
We evaluated the incredible developer discipline required to maintain one-to-one feature parity across diverse languages, specifically praising the Bash implementation's reliance on JQ to ensure structural integrity while understanding the contextual safety reasons for omitting standard shell protections.
And finally, we explored the fascinating paradigm of executable governance, seeing how EAV-structured metadata files allow CI/CD pipelines to natively query rules regarding error registries and deprecated modules.
It has been a deeply technical and revealing audit of an architecture that fundamentally challenges how we think about data storage.
Which leaves us with a final concept to mull over as we wrap up. At the beginning of this deep dive, we talked about how traditional databases are comforting black boxes. We enjoy hiding behind complex query languages and proprietary binary formats because it abstracts the complexity away from us. BJSON forces us to strip away the abstraction and look at the raw, structured data in the harsh light of day.
It demands that we understand the exact shape of our data.
So here is the question for you to ponder. If an entire relational database can be built in plain text so efficiently that an autonomous artificial intelligence can natively read, understand, and safely modify the state without ever needing to learn a secondary query language, are we currently approaching the end of proprietary binary database dominance?
That's a huge question.
In a fast approaching future where AI agents write the majority of our code and manage our backend systems, perhaps absolute transparency and readability will become infinitely more valuable than ultimate compression. Maybe the future of data isn't a hidden, whirring black box at all. Maybe it's an unyielding, perfectly transparent black cube.